So welcome back, and in this short video we're going to be looking at ring activating and deactivating. So the substitutes on the benzene ring can either activate the ring and make it more susceptible to an electrophile, or they can deactivate the ring and make it less susceptible. So any substitute which will withdraw electrons from the ring will make it less susceptible to an electrophile, and anything which can add electrons, push electrons onto the ring, will increase the electron density, making it more susceptible to an electrophile. So we're going to look at some examples of this on page 19 of your notes. So the first example we're going to look at is phenyl methanol, or sometimes known as benzyl alcohol. So this OH group here has a very electronegative oxygen on it, delta negative. And what that is going to do is it's going to pull electrons away from the benzene ring. And that's why it is ring deactivating. So phenyl methanol is less reactive than benzene. So that lone pair on the oxygen doesn't overlap with the ring, and the electronegativity of the oxygen withdraws electrons from the ring, making it less susceptible to an electrophile. The next example we're going to look at is nitrobenzene, and we have a very similar argument. The nitrobenzene, the electrons again are being withdrawn. You've got those oxygens there which are very electronegative, and they will withdraw electrons from the ring. Because the oxygens are not directly bonded to the ring, the overlap of the lone pairs can't occur, because there's no mechanism for the lone pairs on that oxygen to get into the ring. So as those oxygens are not directly attached to the ring, the electronegativity of the oxygen causes the ring to lose electron density, making it less susceptible to an electrophilic attack. And the argument for the chlorobenzene is the same. Again, the chloro group is electronegative. It will withdraw electrons from the ring, making it less reactive than benzene. The chlorine does have lone pairs, but the lone pairs on a chloro are in a higher principal quantum shell than the p electrons in the carbon, and therefore there's not a particularly good overlap. The p electrons in the carbon are 2 p electrons, the p electrons in the chlorine are 3 p electrons, so there's not a good overlap. So they withdraw the electrons from the ring, making it less reactive. So that looks at the electron withdrawing groups, but there are two substitutes which will activate the ring and make it more reactive. We've already come across one of these before, methylbenzene, when we looked at its reactions, but it is electron donating. So that's going to push more electrons into the ring to make it more reactive, or at least more susceptible to an attack by an electrophile. It's the same argument we used when we were looking at the stabilisation of the carbocations. So if you remember back to your lower sixth chemistry, we had an intermediate carbocation, and we said one of the reasons that a tertiary carbocation was so stable was that it had three alkyl groups pushing electrons, or weakly donating electrons onto that carbon, stabilising that positive charge. Well, that's exactly the same principle that's going on this time. My benzene ring is having the electron density of the ring increased by the inductive effect of having a methyl group on there. So that methyl group weakly donates electrons into the ring. And last but not least, we have phenol. Now this is the one you need to star, because this is the one that comes up most frequently in exam questions, explaining why phenol is more reactive than benzene. And it's to do with the fact that this time, unlike chlorobenzene, the oxygen's p electrons are in the same principal quantum shells as the carbons, and therefore they can delocalize over the ring. So you do need to make sure you've got this one almost word perfect. So, first thing, it's the lone pair of electrons on the oxygen can overlap with the pi bonded or the pi cloud or the ring of delocalized electrons. So lone pair of electrons on the oxygen overlaps with the pi bonded system, the pi bonded cloud, or feeds into or donates or interacts with the benzene ring. This increases the electron density of the ring, making it more susceptible to electrophilic attack. You do need to specify that it's just making it easier for the electrophile to attack it. And this is the exam guide answer to this question. So why phenol is more reactive than benzene? Notice the words in bold. So you need to specify it's the lone pair of electrons on the oxygen, not the OH group overlapping. You have to be specific. And this overlaps with this pi cloud, or it feeds in or donates or interacts with the benzene ring. That's your first mark. The second mark is for saying that this activates the benzene ring, it increases its electron density, makes it more susceptible to an electrophile. Quite often this is split into 2 marks, 1 mark for saying it increases the electron density of the ring, and 1 mark for saying it making the attack by the electrophiles easier, or making it more susceptible to an electrophilic attack. Notice again, just making it more reactive is not acceptable. A comment like this, the lone pair of electrons on the oxygen increases the electron density of the ring, would score 2 marks. So that was just a quick video looking at ring activating and deactivating. You must remember, if the oxygen is directly attached to the ring, it will activate the ring, but if there's a carbon group between the oxygen and the ring, it will deactivate. There have been questions in the past comparing the reactivity of phenol with phenylmethanol, where the phenylmethanol is less reactive than benzene, but phenol is more reactive than benzene. In the last section of these notes, we're going to be going on and looking at the reactions of the phenol group in a little bit more detail.